Hi there, this is Robert Bolaños. Welcome to the analysis design of a flyback. This is part 15, and I'll be discussing how to use the PWM model. Okay. Uh, when I'm talking about the PWM model, I did a discrete model. Uh, Let me see if I can find it. Okay, this is the discrete model that that I made in the last video, and this gets to be a little bit too big when you use it in schematic. So there's a way of zipping this up and making it into a subcircuit. Okay, so there's one way of doing that. The other way is using a model that is already developed by Christopher Basso. If you do get the professional version of TopSPICE, it is included in the library. And basically, what I've derived is very similar to what Christopher has derived. There's some minor subtleties. Okay. Now, for those who have asked or will ask for this particular model, I will send you this model. Okay. And if you notice, it says PWM CM2. Okay. Now, to look at the subcircuit, you go to Project, Page, and go to Next. So this is page 2. Okay. So the model or the netlist I have pasted on the second page. So if you're interested, you can take a look at this model. Okay. Now, one of the things that I want to do is I want to look at this, some of what is called the parameters of the subcircuit. Okay. So this is the area that I want to take a look. It is the params. Okay. This tells you the ref is the internal reference voltage that it will be using. This is the period. The default is 5 microseconds. And the maximum duty cycle is 0.5 or 50%. And then there's the ramp and other parameters. Okay. But the most important are the ref. So I would suggest leave that alone. The period, let's go ahead and change it back to 10 microseconds. 10 microseconds translates to 100 kilohertz. So you can double click, change that to 10, and make sure that the duty cycle, the maximum duty cycle is 0.5. Okay, so now it's 10 micro. So those are the main parameters that really affect how the PWM works. Okay, so to get back to the schematic, go Project, Page, First. Okay. Now remember, on the netlist it said period equals 5, and then I changed it to 10. Well, by double clicking on the symbol and putting period equals param, you can change this param. You can change it to 5 microseconds, which would be the equivalent of 200 kilohertz. So in this case, we're going to go ahead and leave it at 10 microseconds, which is 100 kilohertz. Okay. Now the other thing that I want to make you aware is that there is two loops. There's a current loop, which goes into this line that says sense. It's actually the current sense. And then you have a voltage feedback loop. which is this line, and these two resistors, and this FB is your feedback. So this is your voltage loop. Okay. And typically, going back to the current loop, when you hit 1 volt, it resets or turns off the output to the MOSFET. Okay. So let me go ahead and run it. And these have basically the same values that I've derived before. And what I want to show is an important concept as far as how to correctly set the current loop. Okay, because you might end up having problems where it doesn't regulate, and you might spend a couple of minutes to an hour trying to figure things out. So here's an example. It is simulating. Okay, now mind you, it's supposed to be regulating close to 12 volts. Okay, and if you look at the output, if you come up here, is 11.5 volts. So it is not regulating at the 12 volts. Okay, if you notice that, it's not regulating. Okay, so let's go back, and this is just for those who haven't completely seen all of the videos. Just recall that the duty cycle is 46%, or at least that's the assumption, and this is based on the data sheet. Of your PWM. Okay, so what you want to do is you want to look for the maximum. So that sets your duty cycle. And your efficiency for a flyback, 80% would be a good assumption. Okay. Continuing on the previous videos, we calculated what the input power would be. Basically, this is your V out, and this is your I out. And multiplying these two terms gives you your output voltage, or I'm sorry, your output power. And if you divide it by the efficiency, you should get a input power of 7.5 watts. Okay. After you have that, you can go ahead and divide by the minimum voltage, which is 24 volts, and the average should be about 312 milliamps. Okay, and then you calculate your peak current, and that's going to be 312 milliamps, which is your average, divided by, this is a constant, which is 0.5, and then again your duty cycle. In this case, I should get a peak current of 1.35. So what does that mean? Okay, it means that, change a different color, that when the gate or the MOSFET is on, the current should look like that. Okay. This peak is 1.35 amps. Okay. Okay, so that means that this current going through the MOSFET will peak at 1.35. Let me go ahead and put that. 1.35 amps. Okay, make sure that yes. Okay. Okay. So let's look at the SPICE simulation. If you look here, this current that goes through the MOSFET is the current going through the primary, which is L1. So we look at I of L1, and if you notice, it's not exactly, it's just shy. It's 1.25, slightly shy. Okay. So what does that mean? Okay. Well, that means that the current is roughly about what we calculate. It's very close. Now keep in mind that that current is going through the MOSFET, but then it's going through this resistor, and this resistor is a current sense resistor. Okay. So theoretically, if you have 1.35 going through the MOSFET and it's going through this resistor, then this voltage at this node or across the Rsense should be 1.35 volts. Okay, so that 1.35 volts comes here, and it gets divided down a little bit. Okay, so let's kind of calculate that. It's 1.35 times 5 divided by 6. So you're going to get 1.125 volts. Okay, so basically when you get a current peak of 1.35, you will get a voltage peak of 1.1225 here. And keep in mind that this iSense trips at 1 volt. Okay, and if you notice here, I have iSense. Okay, let's look at what iSense is doing. iSense shows that my voltage is exceeding 1 volt, or actually it's clamped at 1 volt. So basically what it's telling me is that this current is higher and the PWM is turning off before it has a chance to get all the way to 1.35. Okay, so how do we set this? Well, we set it by either changing this, the ratio of this, or changing this. So let's go ahead and calculate what the Rsense should be. Okay, so the Rsense, a good rule of thumb, okay, would be to set your Vsense, or I'm sorry, let's go ahead and call it Vsense because it is a voltage in a way. Okay, you want to set it to about 90% or 0.9 volts. Okay, so that means you want Rsense divided by your I peak. Okay, so in this case you want 0.9 volts to appear across the sense resistor when your peak is 1.35 amps. Okay, so let's see what that is. 0.9 divided by 1.35. So we need a 0.66 ohm resistor. Okay, so let's do that. So we'll set this to 0.66, and let's go ahead and remove this resistor. Okay, and let's resimulate it. Okay, now as you can tell, if I zoom here, it's regulating. Okay, slightly above the 2.12 volts, which is good. Now we can take a look at here. This is the voltage sense. Okay, let's see what the peak is. Not quite 0.9, but it's 0.817, which is good. And then we'll measure the current. This is the current through the inductor, and it's 1.29. Okay, so that looks very good. So now you can tell that it's regulating, and you have enough margin that if you need extra power, that it will provide that power because you have a margin from 1 to here. So basically you have 20% margin, okay, which is good. Okay, so that's one way of setting the current source, or actually the current sense resistor, which is this part. Okay. Now another question that they've asked, some of the viewers have asked, how do I implement multiple output voltages? Okay. Now keep in mind, this power supply is designed for, 6 watts. Okay. So let's divide this and make it a 2 output source. So basically I can copy this, paste here. Now you have to rename these. I'm going to put this as out, and this is out 2. Okay. And keep in mind that the power dissipated on both windings have to total 6 watts. So that means this, if we make these 12 volts each, then the current has to be half of this, which is 250 millivolts, and so does this, 250 millivolts. So let's go ahead and just change this to 48 ohms. Okay. So 12 divided by 250 should give you 3 watts, and this should also give you 3 watts. So we're almost there. Okay. Now, if you notice here, the K1, L1, and L2 means that this inductor is coupled to this inductor, but this is not coupled. Okay, so how do I couple it? Well, what you do is you double click on the K1 and you type in L3. Okay, now you're ready. Okay, so let's go ahead and add V out2 okay, and took quite a bit time to simulate, so let me go ahead and put 1.5, see if that's good enough. So now you have a 2 output. We'll resimulate it. Okay, simulate it a little bit longer. Okay, here's another simulation trick. You can reduce the capacitance. That way, with less capacitance, it charges much faster. Okay, let me go ahead and put this back to 1. Okay. So let me go ahead and save this just to show. Save. So this will show you the difference, how making these capacitors 10 times smaller actually reduces your simulation time. There. Okay. So now if you notice, you have V out and V out 2. Compare that with the previous. You can see that it converges or simulates or goes into steady state at a much faster time. Okay. So that's the concept of doing this. But let's say that I want this at 24 volts. Okay, again, it's 3 watts divided by 24, so the current should be 125. Again, it's supposed to be 3 watts, and 24 divided by 0.125, the resistor would be 192. 92. Okay, let me just make sure. Yep, 310 by that. Okay, so we're almost there. Now the thing is, now we've changed the turns ratio. Okay, what do you mean by the turns ratio? Okay, well, the turns ratio is defined by V out, V in. Excuse me. So in the previous, on the first winding, it's 12 volts divided by 24. You had a turns ratio of 5. Okay. So now the ratio is a little different. It's 24, which is the output, new output, and 24 volts is the new input. So we have to have a turns ratio of 1. Okay. So now if you notice here, it says NR1, no, it says NR times NR times LP. Let's change that to NR1, NR1. Okay, so basically we have a new parameter and we defined it here. Real simple. All you have to do is copy, paste, and rename it as NR1 is equal to 1. Okay, so now this NR defines the turns ratio from here, from this winding to this, and NR1 defines the ratio from here to here. Okay, so now if everything's correct, you should see a voltage at 24 and at 12. Again, the total watts should be 3 amps, 3 watts, and 3 watts for a total of 6. There you have it. So we look at here. This is at 12.5, and this is at 25.8 volts. Okay, again, the current stays about the same, 1.33 amps, and the voltage or the Rsense is close to 846. Again, simulating correctly. Okay, and for right now I was going to go ahead and talk a little bit about this part. We've already discussed how to implement the multiple outputs, but I'll go ahead and I'll discuss this in the next video. Okay, so if you have any questions, feel free to drop me a email at rbola35618@aol.com. If you would like a copy of the SPICE model or a copy of my notes, drop me an email and we'll send you my models and notes. Thank you for watching.